Alright, so in the first part of the video when we looked at our different statistics, we saw it was somewhat normal, somewhat of a normal distribution of the statistics. So all the little statistics were somewhat normally distributed, kind of made a normal curve. Still pretty spread out, but they did somewhat kind of form that pattern. And we also saw the mean of all the samples. So mean of all the statistics was close to the parameter, really close. So we're going to try to do this with a somewhat larger number of trials. So instead of doing 20 flips at a time, we're going to do 100 for each group. And let's see what is different. So we're going to assume that we hopefully get something that looks still normal, because we saw with 20 we got a normal curve. But let's see what happens when we do 100 in our sample. So now instead of doing 20 flips for each little statistic, we're doing 100. So if I flip one, so the first one I had 53 successes and 47 failures, or 53 heads and 47 tails. So that's a p-hat of 0.53. So what I'm going to do is I'm just going to go ahead and do 100 samples. And what you can see is you have a lot more different numbers, because with 100 flips you get a lot more variety of statistics than you can with 20. But I wanted to notice something just with these first 100 flips. Still kind of see this normal curve. I mean, it's not perfect, but it's still pretty normal. But in the last one, when we did 20 flips, remember we saw some that were down here like 0.2 and some that were up here at 0.8. You really don't have too many of those. They're much more compact. So this actually is showing that our sampling variability, how far all these different ones are spread out, is much less with the sample of 100. You could also see our mean 0.499 really close to 0.5 really quickly. So if I do 1,000 more, you still see this nice normal curve starting to form, but I still see nothing at these ends. So it's much more compact. Now if I do 10,000, if I do 20,000, you'll see you get a really nice looking normal curve. But the key is, the more times we flip, the more things we have in each individual statistic, the closer together that normal curve is going to be. They were both normal curves. This was just much more compact. And that is actually to our benefit. So what we can see is it's still normal. The mean is still close to the parameter, but it is much less spread out. And that's a good thing, because we want things to be less spread out, because the less spread out they are, the more consistent they are, the better it is to do some of our things we will do with these in the future. So we kind of know this is kind of definitely kind of a normal curve with these kind of properties. Okay. So in general, if you're asking, how good an estimate of our parameter are our statistics? Well, what I would say is one statistic. So if I just do a single statistic, it may or may not be a good estimate. So if I just do one statistic, it's not a great estimate. But if I do the average of many statistics, so if I do it over and over again, like I did on that little that program, the average of many statistics will be a great estimate. Now the problem is, and this is why this is not super efficient, it's kind of a pain to go and take a population and sample it over and over again. In general, in statistics, we want to take one sample and use that one sample and that one statistic to say some stuff about our population. So that's what we will eventually get to, but we start with just kind of looking at how they lay out. So that's going to kind of bring us to these sampling distributions, right? So sampling distributions are going to be all the possible values of the statistic and how often it takes these values. So what we did in this kind of program over here this normal curve looking thing is a sampling distribution. Because if I say 0.5, we can see how many times did 0.5 occur, and how many times did 0.6 occur, how many times did 0.51 occur. So we're seeing how often it happens, or all the different values, and how often it happens. So that is what a sampling distribution is. And we'll do specific examples of a sampling distribution for a proportion, a sampling distribution for a mean, a sampling distribution for the standard deviation. Every statistic and parameter pair is going to have its own sampling distribution, but we can figure out how these relate its statistic to its parameter. So just in general, they will be normal in a lot of cases with some conditions. And in general, the mean of these sampling distributions will be the parameter. Okay, so we'll write that down. We'll say, in general, the mean of the sampling distribution, which is what we found on that little program, is the parameter. And the more in each group, or each sample, the less sampling variability we see. Because remember, with the 100, it was much more compact than it was with the 20. So that's what we like to see. So again, so now we have these two big problems we've now addressed in this course. We have bias and variability. So in general, the way we're going to try to sample is to remember, to avoid bias, we want to use random samples. And to reduce our variability, remember, we want to have larger samples. So this is a really, really key thing in statistics. You always want to have random samples, and you always want them to be as big as you can. Because the bigger these samples get, the less variability you have. Thus, the closer they're going to mimic that actual parameter, which is the whole purpose of this last part of the course. The whole last part, we're really trying to talk about these parameters eventually when we don't know them. Okay. All right, if you have questions, obviously let me know. But we will see these in action for proportions and means in the next couple sections.